Hi everyone. Today we're going to be talking about volumes of solids of revolution. So first, we should probably define what that means. Essentially, to find a solid of revolution, what we do is we take some area here. Maybe we'll say, this nice area right here. Nice and shaded area. And I'm going to form a solid by revolving this around the x-axis, kind of spinning it as it were. And when you do that, what happens is you get this nice shape. The same exact copy of the area here appears right below it, but you're revolving it here. So you get this nice conical shape here. And what we'll do is we'll use the properties of integration that we've seen in the past to help us calculate volumes of these solids. And we're going to do it in a really, really cool way that maybe we haven't seen before or thought of before. So let's first start off with some equation here. So let's do a nice basic one here, and let's do exactly what we had drawn there a second ago. We'll do y equals x from 0 to 2. This is going to be our region. So that looks like this nice triangle. Great. This is 2. That's 0. All right, awesome. So what we're going to do here is we're going to revolve this, just like I said. We're going to revolve it around the x-axis. Okay. And so when we do that, because this is a triangle, if you imagine spinning it, really what we're doing is we're just spinning this one line around the x-axis, and we're going to make this nice cone right here. Great. There's our cone. The question is, what's the volume of it? Well, to do that, we're going to use something called cross-sectional areas. I'm going to start abbreviating this CSA so that I don't have to write cross-sectional area every time. But cross-sectional area essentially just means what I'm going to do is, rather than calculate this as a volume in one go, it's a little bit easier to calculate the area of just one of the cross sections. And by cross section, I mean, imagine you're just taking as thin a slice as possible. What shape would you end up with? And in this case, you can notice that, oh yeah, I'd end up with a circle here. If I sliced it a little bit thinner, not thinner, but a little further to the left, I'd end up with a smaller circle. Every single time I slice this, I definitely end up with a circle, which is pretty cool, as long as I'm slicing it perpendicular to the x-axis. And that's how we're going to think about slicing it in this particular example. So if I'm slicing here, I get a bunch of circles. Circles, I know the area for, right? So my cross section, it looks like a circle, and the area of a circle is pi r squared. And you might be thinking, well, why are we talking about areas when this is a volume problem? Well, as it turns out, if I took every single possible cross-section and added up all of the areas, I would just be stacking all of these circles on top of each other. I'd get exactly this volume, right, by adding all of the areas together. And we've seen a technique to add things as they're getting infinitely thin, right? We imagine our slices getting infinitely thin. And that's exactly the technique we used when we transitioned from RAM to the actual area under the curve. And that's going to be the same thing we do here. All we're going to do is take an integral. This will add up all of the infinitely thin areas. The integral will go from 0 to 2, since I decided to bound it from 0 to 2. The function itself should be pi r squared, right? We're adding up all of these areas. And the question is, what's r? Well, if I look at my drawing, if I chose a random spot to cut this cross section, the radius of this circle would be from here to here. In this case, that distance is just x, because this is the y value corresponding to this random x value, x. So in this very specific case, my integral looks like this. The integral from 0 to 2 of pi x squared with respect to x, right? Great. So when I integrate this, the pi is just a constant. The x squared becomes 1/3 x cubed, and I go from 0 to 2. So I'll plug in 2 for x, and I'll subtract when I plug in 0 for x. When I plug in 0 for x, I just get 0. So this means it's pi times 8/3. And of course, my units are cubed. Units cubed. Great. Cubed. Awesome. So let's do a little common sense check. This shape is a cone. The volume for a cone is 1/3 pi r squared h, where r is the radius of the base and h is the height. Well, if I look at this, the radius of the base right here, that's 2. The total height right here, that's also 2. So I can plug in 2 for r and 2 for h, and lo and behold, I'll get out 4 times 2, 8, 8/3 pi units cubed. Great! So I got the same answer both ways, so this is good. Good common sense check. What I'll do right now is I'm going to outline a quick procedure for how we'll handle these problems, no matter what the problem is. I'm just going to outline step by step exactly what I did here. So the first thing I did was sketch the solid. This is always a really great thing to do, just like we saw in an example not too long ago when we were asked to integrate the square root of 9 minus x squared, and we couldn't. Drawing a quick picture would have made that very easy just by finding the area of that semicircle. The second thing that we'll do is identify the shape of the cross section. Occasionally they won't be circles. Generally they'll be very close to circles because of the way that we're constructing these solids. Third is going to be find the cross-sectional area, which I said I'll abbreviate CSA. And then finally, integrate that cross-sectional area. So this is going to be our general procedure right here. Whoop. And let's try it out on a new problem. This one was a particularly nice problem because we could find the volume in 2 ways. But in fact, it's kind of silly to do it this way when we can already do it like this. So let's consider a new solid that maybe we don't already have a formula for. We're not going to get too crazy with our functions in this intro, but we'll get a little bit crazier as the familiarity with this stuff increases. So let's say we have y equals x squared. And we'll just keep it from 0 to 2. Does that sound reasonable? Yeah, that sounds okay. Great. So first I'm going to sketch this. From 0 to 2, looks like that. This is the point 2, 4. I'm going to rotate this about the y-axis. About the x-axis. And when I do that, I end up with this shape, which kind of looks like a cone, except these aren't straight lines here. They're nice little curved parabolas. Okay. And so the question is, first, what is the shape of the cross-section? Shape of the cross-section. In this case, again, it's a nice circle. Whoop. So I know the area formula for the circle is pi r squared. So now I'm going to add all of those areas together. I'll go from 0 to 2. I'll get my pi. The radius of any random cross-section. So if I'm at some random point here, x, the value of this radius is x squared. And remember that it's x squared squared because it's the radius squared. Great. And then from there, the integral is not too bad. X squared squared is just x to the 4th. So I can integrate this without too much difficulty. This should be pi x to the 5th over 5 from 0 to 2, which is just 32 pi over 5. And I'll have my units cubed because it's a volume. Great. Hopefully that's not so bad. And now we're going to make it a little bit more interesting, because this has been boring, right? I've just been rotating it around the x-axis, and it's been sitting on the x-axis, so every single time it makes a really nice shape. I'm going to make it a really nice shape again, but in this case, it won't look quite like how it just looked. So let's do one of these guys here. Let's say I have exactly the same curve, bounded exactly the same way, but instead of rotating it about the x-axis, I'm going to rotate it about the y-axis. Okay? And that will give me this shape, sometimes called a paraboloid. It's a 3D parabola, which is pretty cool. And I want to find the volume of this shape. Well, what's tough is that if I made the cross sections in the same way as before, perpendicular to the x-axis, they'd now be a bunch of parabolas. And so that's really tough because I don't know how to find the area of a parabola, the area inside that parabola. Because to do that, I'd have to integrate an integral, and that would be tough. What's a little bit nicer is if I make slices perpendicular to the y-axis here, each cross-section will be a perfect circle. So this is what I'm going to do. I'm going to make my cross-sections circles, because circles are awesome. And so to do that, I'm going to slice perpendicular to the y-axis. So my cross-section is a circle. The area is still pi r squared. I'm going to take my integral. I want to think about, okay, what's the radius of this random circle here, somewhere in the middle? Well, you might be tempted to say that it's x squared, and then we do the same thing as last time, but that doesn't quite work out, because if you want this to be x squared, which you could totally say, when we add up the areas of the circles, we're now adding from the bottom all the way up to the top, from bottom to top. Great. And the problem is, before we were adding from left to right, which made total sense to be integrating with respect to x. But since we're now adding from bottom to top, we're going to be integrating with respect to y. These circles are going to be changing based on your change in y. If you wanted to integrate with respect to x, then we'd get those parabola things again, and that's not so great. So what I want to do is I want to rewrite this radius as a function of y. So rather than y equals x squared, I'll think about it as x is the square root of y. And now x is just the positive square root of y, since I'm going from 0 to 2 in this particular case. Sometimes you might have some other ones. Turns out that it won't matter in this case because we're going to be squaring it. And then the last point worth making here is our bounds, right? They shouldn't be 0 to 2 anymore because those are bounds on x. They should be from 0 to 4 because remember this is the point 2, 4. Great. Square root of y squared is just y. So this integral becomes pi times 1/2 y squared from 0 to 4. Again, we have the same thing. Plugging in 0 makes it 0, so subtracting 0 means we can just plug in that 4. 4 squared is 16, divided by 2 is 8. This volume is 8 pi units cubed. What's really nice about this answer is that it's a lot bigger than that weird cone shape that we had in the last example, which is good. This is a bowl. It's pretty big compared to that cone, which was big at some points, but generally pretty small. So this is a bigger answer. That makes some good sense to me, hopefully to you as well. We're going to do 2 more examples together, and then I'll give you one to work through on your own to end this video. So let's say now we know how to do this revolving it around the x-axis, also revolving it around the y-axis, but we've been really, really nice. Each time that we've done that, we've kind of sat things right on the axes. The region's been right there. So let's do one quick example where we're a little bit off what we're revolving about. Let's say I want to find the volume of the solid generated by revolving the area beneath y equals 3, and we'll go from 0, and we'll go all the way up to, oh, actually, you know, let's not do 0. Let's make sure it's not touching any of the axes. From 1 to 4, excuse me. So let's say from 1 to 4. And we're going to revolve it about the line y equals -1. Okay, so to do that, here's my 3 from 1 to 4. So it should look, oops, like a nice horizontal line there from 1 to 4. And I'm revolving it about this line here, which is y equals -1. Okay. Oh, that looks bad. Y equals -1. Great. When I do that, I'll end up with its mirror image kind of down here, and it'll be connected to make a nice cylinder here. Now again, this is a little bit of a silly example because I can figure out the volume of a cylinder, but just for the sake of doing it with the integrals, we'll make sure that this matches our conceptual understanding. So this particular solid, cross-section area. Well, the cross-section is just a circle, again, if we're cutting it perpendicular to the x-axis. And we know the area for a circle is pi r squared. We've done this a few times now. And the question is, if I took a random slice, what's the radius? Well, in this case, the radius is 4. Because going from -1 all the way up to 3 means your radius is 4. So this is an integral from, whoops, not 0 this time, from 1 to 4 of 4 dx. That could not have been more wrong. It's not the integral of just 4, right? 4 is the radius, pi times 4 squared. Great. And this will give us, well, that's 16 pi, and that's just a constant, so that means its integral is 16 pi x, and we'll go from 1 to 4. And we'll just plug in our bounds and see what we end up getting here. Plugging in 4, I get 64 pi, and subtracting when I plug in 1, which is 16 pi, I'll get a final answer of 48 pi, and that's units cubed. 48 pi units cubed. And we can test this out the other way, too. We know that this is a cylinder. We know the volume of a cylinder can be found using pi r squared h. We know that r is 4. The height from the bottom to the top is 3, because I'm going from 1 to 4. So that means that's just pi times 4 squared times 3, which again is 48 pi units cubed, which is awesome. Drawing this picture, I cannot emphasize it enough. It is very easy for you to think that the radius in this case might be 3, or to not quite fully think through exactly what this solid is going to look like. Drawing it out helps so much, and you're about to see another little bit more exciting example here where drawing the picture is especially helpful, because we're going to get to our first one where the cross-section is not a circle. So, let's say I have the following region. It's the region bounded by the y-axis, the line y equals x, and the line y equals 3. So let's sketch this region. Here's the line y equals x, here's the line y equals 3, and here's the y-axis. So here's my region here. I'll call it R, and I'll just erase every part of it that I don't need for this particular drawing. There's my R. And I want to revolve this about the x-axis. Revolve this about the x-axis. So when I do that, I'll get its mirror image down here, and it'll be connected like this. So this is kind of an interesting solid. You'll notice that it's a cylinder, right? That's what happens when we revolve y equals 3, just like in the last case. You get this cylinder, but then you're missing this cone is kind of taken out of it because this region here, this nice big triangle, isn't filled in, right? It's not part of our region. So, what does my cross section look like? Well, if I took a random cross section, I would get something kind of interesting here. This top piece gets connected back to this top piece, and this bottom piece also gets connected to this bottom piece. So if I'm revolving it around, you'd think I'd get a big circle from the top and the bottom, right, connecting to each other. I get this big circle, and then I get a smaller circle connecting these insides here. So what I end up getting is something that looks like this. And we generally call this a washer. If you ever put together some furniture at IKEA or just had to use some tools for whatever reason, you might recognize this as looking exactly like what we call a washer. To find the area of the washer, what I do is I take the big radius, which I'll call capital R, and the small radius, which I'll call lowercase r. The area of the washer is the area of the whole circle. Take away the area of the small circle. So it's pi r squared minus pi r squared. Big R for big circle, little r for little circle. Okay. And if I wanted to factor this out, I could. It's pi times r squared minus r squared. What I can't do is factor out the squared, right? That's not how exponents work. So please, you can leave it like this if you want. If you really wanted to and recognize that this is a difference of squares, you could factor it further, but it's generally not going to be very helpful for us. Okay, so let's calculate this. I'm integrating. Well, what are my bounds here? They weren't given to me, but I can figure them out. 0 is the starting x value. The ending x value is when the line y equals x is the same as the line y equals 3, which happens at 3. So I'm integrating from 0 to 3. And let's see here. How do I want to proceed? Well, I noticed that my slices are moving from left to right. So this is definitely an integral with respect to x, which is awesome. I need to identify my big R and my little r. My big R, I find by drawing a line from the axis of revolution all the way up, the furthest it can go out. In this case, that big R is 3. But little r, well, again, I'm going to start here, but instead of going all the way up to the top, I'm trying to figure out what I'm subtracting out. So I'm subtracting out this tiny cone, and the cone has this radius here, and this radius happens to be the line y equals x. So I get this fun little integral. And I can integrate this if I really wanted to. Pull out the pi all the way out to the front. The integral of 9 is just 9x. The integral of negative x squared is negative 1/3 x cubed. So this becomes pi, and then times 9x minus 1/3 x cubed. And I'm going to evaluate that from 0 all the way up to 3. And when I do that, let's see what I get. I'll plug in 3 for my x's. I'll get 27 minus 9. When I plug in 0 for my x's, everything cancels. So this is just going to be 18 pi, and it'll be units cubed. Now this was a particularly nice example that we could really see, because if you recall, we just integrated, found this volume of the solid of revolution with the line y equals 3 in our past example, And even earlier than that, we found y equals x. So we were able to really see the two shapes, a cylinder and a cone, and recognize that we're taking our cylinder and subtracting away the cone. Okay. So this is called the washer method in general. We'll look at some other methods for how to find volumes of solids, maybe later on, but if you could, kindly try this problem. Let's say I want to find a volume of a solid. Makes sense. And this particular solid is bounded by the following curves. It's bounded by y equals the square root of x. It's bounded by y equals 0. And it's also bounded by x equals 1. And just for kicks, we're going to revolve this about the line y equals 2. So what I'd like you to do is start by drawing a picture, and then figure out the cross-sectional area, and then integrate. Setting up the integral is most of the battle. Hopefully by now we're pretty comfortable with techniques for anti-differentiation, but we'll see as we get more complicated, some of these things will start involving U substitution and trig antiderivatives, so make sure that we brush up on those. Try this one out, and I'll see you in class tomorrow.